Hey everyone, good to have you back on our series on statistics. This is episode 4 and we'll be adventuring through summary statistics. Data is all around us. There's often too much data to handle and it gets in the way of making useful conclusions. But what if I told you can summarize an entire array of data into one single number? That's what we'll be exploring today. Summary statistics summarize a set of observations to communicate the greatest amount of information as simply as possible. So in this episode, we'll be adventuring through 3 major topics. 1. Measures of locations such as mean, median, and mode. 2. Measures of dispersion such as variance and standard deviation. And finally 3. The difference between population and sample. So the easiest way to summarize data is to try and find the central tendency. As the word suggests, you want to find where the data tends towards. I'm sure you might be very familiar with the 3 measures of locations, but make sure you look out to how we express it mathematically and how it relates to the distribution functions we learned in the last episode. So let's consider an example of a discrete random variable x. So we would have learned how to take an average, which is just to add up each individual outcome and divide by the total number of outcomes. But what if there were the same value many times? And what if there were more than 100 of different values? Will we just sit there and add up every single value to find the average? A better method is to calculate the mean using the expected value or expectation of the random variable. The expected value, denoted E of x, incorporates the relative frequency or the probability of each outcome occurring. So to calculate the mean, you just need to multiply each outcome with its associated probability and add them all up. This helps us speed up the calculation rather than sitting there and adding up every single number. So we can derive a formula for the mean denoted by mu that looks like this, which simply adds up all the products of each outcome and probabilities together. Now, considering the continuous case, we just need to consider every pair of outcomes and probabilities. We use integration, which can be thought of as an infinite sum, and the probability can be derived from the PDF instead. Now, the next point is the most important point in this episode. The expected value is equal to the sum of the product of each outcome with its probability. So the expectation of any expression, say triangle, is the sum of every triangle multiplied with the probability of the triangle occurring. We briefly touched the median in episode 1 from box and whisker plots. The median is simply the middle number in terms of its position, not its size. The random plus a half confuses many students, but it's because we're not looking for half the population size. Please note that if there's an even number of data, then we take the average of the 2 middle values. Now, in a continuous sense, the median splits the population into 2 equal parts. That means 50% of the data will be below the median and 50% will be above the median. So letting the median be m, the sum of the PDF from the first value to the median will represent 50% of the population. Similarly, we can consider looking for m when the cumulative probability reaches 50%. The mode is the most frequent outcome. In a discrete sense, you look for the outcome with the highest frequency or probability in the table. In a continuous sense, you look for the highest peak on the PDF. This can be achieved by considering the shape of the PDF or calculating the absolute maximum via differentiation. The other major type of summary statistic is known as measures of dispersion or spread. Rather than looking for the middle, we want to quantify how spread out the data is. The approach will be very similar to least squares regression we used to calculate the line of best fit in episode 2. Deviation means the difference between the actual data and the mean value of the data. Now, if we take just the deviation by itself, positive and negative deviations will cancel out, so that won't be too meaningful. So we consider adding the squares of each deviation because it won't cancel out and the larger deviations will have a greater impact on the variance. Variance, denoted by sigma squared or var x, is equal to the expected value of the squared deviations. This is the second most important point of this episode, so ingrain this to your brains. Now, since variance is a squared measure of deviation, if we square root it back, this just results into what we know as our standard deviation. I can completely understand that this formula turns people off from maths, so let me give you a simple example with 3 easy steps. Number 1, you need to calculate the median first. Number 2, then we calculate each of the squared deviations from the mean. And finally, number 3, calculate the expected value of the squared deviations. In a continuous sense, it's the exact same process but using integration as we're adding up all the infinite squared deviations. Now, a huge disclaimer. You will see the mean and the variance quoted as simple averages like this. It is acceptable, but again, you need to sum every single value or every single squared deviation and then divide by n, which for small datasets is very useful, but for large datasets will not be useful. What we have learned today is called the expected value or the weighted average, as they account for the probability of each outcome. That means we can now form a relationship between the mean and the variance. So the variance, again, is the expected value of the squared deviations. We can expand the quadratic inside, and then split the expectations. Since mu, the mean, is a constant, the expected value of mu is still just mu. Now with this relationship, we can simply calculate variance algebraically rather than through the messy table. A population represents every element of the entire cohort. A sample is a subset of that cohort. The reason why we make such a big fuss is because often at times it is difficult to obtain the characteristic for every single element in the population. For example, to find the average height of Australians, you would literally need to ask every single person in Australia. Hence, to overcome this challenge, we predict characteristics of a population by sampling. So there are some differences in notation and formulae used between populations and samples. Number one, a measurable characteristic of a population is called a parameter, whilst a characteristic of a sample is called a sample statistic. Say we measure the mean of a population. This is a parameter called the population mean. But the mean of a sample that we surveyed is a sample statistic, also known as your sample mean. Secondly, let capital N represent the total number of elements in a population, and little n represent the number of elements in a sample. Because we are considering each individual element, we'll go back to calculating the individual values rather than taking expected values. The population mean is still denoted mu and adds every element and divides by capital N. The sample mean, however, is denoted x bar and adds only the elements in the sample and divides by little n. Finally, 3. The population variance is denoted sigma squared and adds every squared deviations and divides by capital N, still the same. Now the sample variance denoted as squared is unfortunately slightly different. Dividing by the total squared deviances by n creates a biased estimator. Don't worry about the definition as it's outside of the syllabus. So to find the unbiased sample variance, we add up all the squared deviations but divide by n-1 rather than n. So that's it for episode 4. We learnt about summary statistics and the difference between population and variance. Otherwise, tune in to the next episode to finally tackle normal distributions, or click here to watch episode 0 on the big picture of statistics. So like, subscribe, leave a comment below on what you would like to learn in the future. I'll be there.